Today we're going to do more friction problems, and this will probably be our last friction video. So we're going to have a sled and a rider sitting in the snow. So here's our sled, and there's a person on there. And we want to push the person. So let's see what we know. mg goes down, normal goes up. We're going to push or pull, it doesn't matter. It's going to be in that direction. I know there's a little typo up there, sorry about that. Now since we're starting to move the sled, that's static friction. The sled and the rider aren't going to come off the ground. They're going to stay sitting there. So the sum of the forces in the y direction has to be 0. Bring the 0 down. Normal goes up. mg goes down. Normal equals mg. And just to remind you, normal is pointing in the positive y direction. mg is pointing in the negative y direction. That's why they're positive and negative. And since this is 0, I just move the mg over. Now in the x direction, the sum of the forces, make that an x, is still 0. You might say, well, why is that 0? We're not accelerating yet. We're just trying to get it rolling. If you remember, there was that spike. That was the static friction that we had to overcome. So we haven't really got the sled, fully underway. We're just trying to overcome that static friction, just sort of the tipping point. So that's why we make that 0. So 0 equals force of pull equals force of pull, because that's in the positive y direction, minus the static friction, which is in the negative direction. So let's move the force of the pull, because that's what we're interested in. It's friction static. Now friction static is mu s times the normal. Friction is always mu times the normal. But we said over here, hey, normal is equal to mg. So mu s times mg is the force of the pull. Once we've done the algebra to that point, it's pretty easy. Mu s is 0.15. That's not unreasonable for snow. It's not quite as slick as what ice is. The mass is 50 kilograms. Now that would be a pretty heavy sled on its own, but this one has a rider on it, so there's a child sitting on it. And of course, gravity is always 9.8 meters per second squared. Mass is kilograms. And if I punched it right in my calculator, I'm getting 73.5 kilogram meter per second squared. And to remind you, that's 73.5 newtons. I have the wrong, this little mark shouldn't be here. Let me just rewrite it. 73.5 newtons, get rid of that. I don't want to take the time to erase now. So that's how much force you would need just to get it moving. Now, if you could keep applying that force, we'd be into the kinetic friction range there, and we might be able to go a little bit faster. And let's see the hockey puck here. A hockey puck slides on a skating rink. We know the mu k, and we know the initial speed. This is after we've hit the hockey puck, because it doesn't say anything about a force of the pull or force of the hockey stick. So mg goes down, normal goes up. Now let's assume the hockey puck, here's the hockey puck, is moving in the positive x direction. Friction always opposes motion. That's our free body diagram. There's only 3 things in the free body diagram. Now you might say, well, what about the force that the stick, when the person hit the hockey puck? That force is only while the stick is in contact with the puck. At this point, it isn't. It's left the puck, or the stick. It doesn't say anything about the hockey stick. right, so let's see what's going on here. The sum of the forces in the x direction will be ma. You say, well, why not 0? There's no other force here, so it has to be, and reasonably, it's going to slow down. We all know that. So ma equals kinetic friction, force of kinetic friction. Now, normal goes up and mg goes down, so I don't think it's unreasonable to say that normal equals mg. So the force of kinetic friction is mu k times the normal. Now watch what's going to happen here. Let's substitute mg. Some folks like to put their numbers in earlier, but here's a case where you really shouldn't. You're always better to leave it in variables as long as you can. Because what do you notice cancels? The m's. And this is real, and I should have the kinetic in here because it's kinetic. Look at that, acceleration is just mu k times gravity. So that's 0.15. Gravity is 9.8. If you do that, you get 1.47 meters per second squared. Now, it says negative in the answer. The reason I made it negative is because it's going to be slowing it down. It's in the negative direction. So sometimes in physics, we always want to check our signs, and we always want to check them at the end to say, all right, is this in the right direction? Is this force going the right way? We also could have put the negative here saying, well, it's slowing down, and then we wouldn't have to worry about that. It would be there all the way through. Maybe that would have been a good approach. Now let's get the distance until it stops. So we know the acceleration, and we know the initial speed, and I think I have a blank slide here for us. So to get the distance until it stops, what we're going to do is we're going to use the time independent. And we'll do a little picture. So we can imagine that the initial speed we were told is 4 meters per second. I'll double check that. Yeah, it's 4. We want the hockey puck to come to a stop. So its final speed will be 0 meters per second. Oh, so that's going to be 0. So acceleration is negative v initial squared over 2x. Distance is x, that's what we're interested in. Negative v initial squared over 2 times the acceleration. Now it's a piece of cake. The initial speed is 4. Don't forget to square it. And of course, that's going to be 16. The acceleration is not gravity. This object, the hockey puck, it's not falling. We don't want hockey pucks to go in the air. We want them to stay on the ice. But we calculated that this is negative 4 meters per second squared, or negative 1.47 meters per second squared. So we can see that the 4s are going to cancel, or the negatives are going to cancel, excuse me. So this will top 4 squared is 16, and 2 times 1.47 is 2.94. And then we do our division here, and I'm getting 5.44 meters. That's 17, 18 feet, roughly. Let's double check here. 4.44 or 5.44 meters. Hockey puck going 17, 18, 20 feet. That doesn't seem unreasonable for this problem.